Okay, so solids have a definite shape, a definite volume, and then you say gases, oh no, they don't have a definite shape and they don't have a definite volume. They can be this big or they can be this big, right? And maybe remember that. And if you think about it, are solids compressible? That's something they don't talk about in middle school. Can you compress them? Can you make them take up less space? And then the question is, why not? Why can't you? And I don't know if you understand what's going on down there at that size, but atoms have an attraction for atoms, don't they? But what if you get them too close? What about my electrons and your electrons? Aren't they both negative? So if I try to push you closer and closer, they might attract each other, but what are the electrons doing? They're repelling, aren't they? It's difficult to, there might be a limit to where you can push them. And so solids really don't have any extra space. So if you try to compress it, you can't. What about gases? You say, wait, I get it now. The reason gases can be compressed because there's nothing between the particles. Nothing, not air. If I have a balloon full of helium, there's not air in between the helium. There's nothing between the helium. Well, I don't understand. Nothing. I get it. What's between a proton and an electron? Nothing? I don't know what that means. We have gases, and we do this all the time. We have a company in Greensboro that sells natural gas, like propane or something like that. Now, we don't want to have a huge truck that has this big amount of gas in there because, number one, it'll hit power wires and it overpasses. You can't. So how do they transport huge amounts of gas across the country? And they compress it, don't they?
Yeah.
And what else do they do? You can use pressure to make it take up space, and what else? There's a special kind of trucks. They are refrigerated. They cool it. So when you cool it, they get closer and closer and closer. And you compress it, they get closer and closer. So you can actually transport a huge amount. As a matter of fact, they compress it so much that natural gases change into a liquid. And then they transport large amounts of it. Then when you get to a place like, have you ever been on I-40, those tank farms? You know what's in those great big white things? Gases. So when you get them there and you want to let the pressure off, whoo, then they take up a lot of space, don't they? All right, so that makes sense, doesn't it? Solids make sense, and gases kind of make sense. Now here's where, did I talk about Goldilocks yesterday? Did I talk about Goldilocks?
I don't think so.
Okay. I got some sad news. You sure? Okay, I don't want to do this twice. I got some sad news for you. Sad. You know the Goldilocks story. Remember they always show Papa Bear's bowl as being huge, right? And when Goldilocks got there and tasted the porridge, Papa Bear's porridge was what?
Too hot.
It was too hot. And then Mama Bear's bowl, which is always shown to be medium size, is what? Too cold. And then Baby Bear's bowl was just right. Well, in the terms of physics, that is impossible. I know why you're too hot. You don't have enough surface area per volume, and you don't cool off very fast. That's why you're still hot. But look at Mama Bear's bowl. It had enough surface area that it completely cooled off, didn't it? Here's what's sad. Here's the sad part. If Mama Bear's bowl was too cold, then what's Baby Bear's going to be? It's going to be cold. All right. I hate to break the news to you, but the reason I bring up Goldilocks is that here's what they do, and I've seen science books do it. I've seen elementary teachers do it. Here's the Goldilocks hypothesis. If solids, the particles are really, really close, and gases are really far apart, then where are the particles in a liquid? And I know you want to say it. Kind of in between, just right. There's a problem with that. Because if that's true, then I should be able to compress water a little bit. Right? I should take a gallon of water and take it into half a gallon of space. If they're halfway. They're not halfway. You cannot compress a liquid. So you can't go to the store and buy, hey, can I get pressurized milk, please? Can I get a pressurized milk? You know, it only takes up half the space in my refrigerator. I just have to be careful when I take the cap off. They don't have that, do they? And what about my car? How can I stop my car? Do you know in my car there's these pipes in there, little pipes, and they're called brake lines? You know what's in there? Liquid, brake fluid. And so what happens is, when I put my foot on the brake, I try to compress the liquid. But you know what? You can't compress a liquid. So what happens is when I push on the liquid, try to compress it, that force goes boom, and it goes everywhere in those pipes. Everywhere. Boom. And when it gets to the part on my tire, it pushes the brake shoes and goes, and that's called hydraulics. And hydraulics are how we have these things, how we have big backhoes and stuff like that. How can you dig that much dirt with a hand, just pushing your hand like that? If you watch a movie and have airplanes going at 800 miles an hour, and how do you turn? You know, how do you make that flap go down like that? Huh? You're going 800 miles an hour. How are you going to make that piece of metal go like that? By hand? Oh yeah, the pilots just kind of they go out. No, they use hydraulics, don't they? So in the movies, when you hear about some plane that's got shot up, and the pilot says, "Uh-oh, we lost our hydraulics." So a bullet came through and went through the pipes that had the fluid in it, and now guess what you have now? You don't have a plane anymore. You can't steer it. All right, it's going through the air. It's got a little bit of lift, but you can't turn it left or right. So now what do? You're probably going to die. So that's what they say when they lost our hydraulics in an airplane. That's bad. That's bad. So anyway, I understand that there is a little bit more space than a solid, not very much. And how do I know that? Because it's non-compressible. So that's the one thing I want to show you that they probably don't teach in middle school, definitely not in elementary school. The last thing I want to do before I do my demonstrations is, did we talk about this yesterday, the kinetic theory? Okay, so let's talk about this a little bit. The kinetic theory of matter says if I take anything, let's take a piece of solid gold, and if we can see the particles, if you're not at absolute zero, you have some kind of motion. Kinetic energy is called the energy of motion. So they have some kind of motion. But what if I were to heat that piece of gold? What if I added heat to that piece of gold? What would happen to the particles?
Get further apart.
They what?
Get further apart.
And why though?
Because it's hot.
As they get more motion, they have more kinetic energy. When they hit their next door neighbor now, they hit them with more energy, and it makes that particle move faster, doesn't it? As they kind of collide with more energy, it moves them a little further away from their next door neighbor. And then you've got a piece of hot metal, hotter metal, and then it gets to a point, it gets to a certain temperature where they're far enough apart to change from a solid to a liquid. Now, what do we call that? Melting. Pretty easy. Now, what if you continue to add heat to liquid gold? Let's continue to add heat to liquid gold. What would you get? They'd move faster, still liquid. They would reach another temperature, not called the melting point, but called the boiling point. And that instead of being a liquid, they now would have no attraction to each other and turn into a vapor, a gas. And you would have vaporized gold. Now, most people don't want to vaporize gold unless you have a way of catching it. And so that's the kinetic theory going that way. Let's go the other way. Let's take vaporized gold and let's cool it. Now what happens? What happens? Yes, and as you take away kinetic energy, they can get closer and closer to each other and turn into a liquid. Now, what do you call that? When you change from a gas to a liquid.
Condensation.
Yes, it's called condensation. Right? Is that right? All right. That's called condensation. Now, which one's higher? The boiling point of a material or the condensation point of a material? Which temperature is higher? What? All right, what do you think? How many people say boiling point? What's the boiling point of water? 100 Celsius, right? What's the condensation point of water? 100 Celsius. Let's keep going down. Let's cool that liquid some more. Cool it some more, and they get closer, and they get really, really close, and they turn from a liquid to a solid. What do they call that? Freezing. Or people don't like to say, I just froze some gold, so they say what? Solidification. Yep. Which one's higher, the melting point of gold or the solidification point of gold? It's the same temperature. Anyway, that's the kinetic theory of matter. Theoretically, any bit of matter can go through these phases. I didn't mention this, I'll mention it real quickly, but we don't talk about it that much in chemistry. But there is actually a fourth state of matter, and it's called plasma. And so what happened is, can you imagine the particles are already kind of far apart from each other, but what if I were to energize them even more? I could reach the point where the atom itself is not holding itself together. The nucleus, which is always positively charged, because that's where the protons are, would not even be associated with its own electrons. So I'd have this hot soup of charged particles, nuclei and electrons. And there are people who actually spend a lot of time studying plasma. If you would like to do some kind of a research thing on this for extra credit, I'm looking for good definitions, maybe some pictures or applications. What are they doing with plasma? And again, if you do something on the net, you always have to highlight the important stuff, okay? But anyway, I think if you wanted to, I'm not going to talk about it very much in this chapter, but plasma is kind of interesting. Yes?
Isn't fire plasma?
Yeah, well, it's possible that parts of fire are some parts of fire. Yes, and how about, what do they call this thing?
Plasma ball.
Plasma ball. So, can you create plasmas that are not super hot? Yes. And what do they do with that? So anyway, if you want to look that up, you say, I'm kind of interested in that thing called plasma. Do that. I want to show you about one more thing. Did somebody else have their hand up and I didn't call them? Show you one more thing. Almost every material, theoretically, they should be able to go through all three phases. But we have some materials on the planet that are kind of odd. Do you know of any object that goes directly from a solid to a gas and you'd ever see the liquid? Have you ever heard of anything like that? I'll tell you, there's a material that you can go get at Harris Teeter normally, but you're going to have trouble finding it in the next 4 days because lots and lots of people are going to buy it. Dry ice, you're right. You can actually buy dry ice down there, but so many people use it for parties and stuff like that. Dry ice is frozen carbon dioxide. It's about minus 110 Fahrenheit degrees. And if I were to set a regular piece of ice here and a piece of dry ice, I would very soon see a liquid puddle of water here. I would never see any liquid here, but the dry ice would get smaller, it would get smaller, it would get smaller. If you put that in a baggie and seal it, Ziploc bag, a little piece, the bag will get bigger and bigger, and it'll eventually pop, and then there'll be no dry ice anymore. And it actually changed from a solid right into a gas, and what's the name of that? I wrote that in here, but what do you call it when an object goes directly from a solid to a gas? Sublimation. It sublimes. There's another material that does this, and it's very common. I actually have some in the back room here, but maybe not your grandparents, maybe, because you guys aren't very old. But if you had great-grandparents, for sure, and maybe parents, not that you should ever go into your grandparents' dresser drawers, but if you've ever gone into your grandparents' place and you smelled a funny smell, especially where they store their sweaters, all right? They were taught by their grandparents or their parents that you could buy these really cheap things called, anybody know what they're called? Mothballs. And these mothballs they are one of those materials that's sublime. So if I leave mothballs out here, very soon the whole room would kind of smell like mothballs, and the size of those mothballs would get smaller and smaller, and you'd never see liquid mothball. So when I first came here, I actually, don't hate me for this, but I started the insect collection thing in biology, and so Ms. Founds was good enough to continue it when she started teaching biology, and I had to talk her into it a little bit, but she loves it now. But do Do you know I can go to some universities and they have an entomology department where they have insects in drawers that have been there for like 50 years. Now, if you tried that at home, it wouldn't work because they're all little tiny insects that like to eat exoskeletons. But what if you wanted to keep these for 50 years? The easiest way to do it is to put a little mothball, put a couple mothballs in a piece of gauze, put them in your collection and put a top on it, and insects hate mothballs. That's why they work for your grandmother. Because you put your sweaters in there, moths are not going to get in there and start chewing on the wool sweaters because they hate that smell. Now, does anybody know what else people did besides mothballs? They put their sweaters somewhere so the moths wouldn't get to them, and they didn't put mothballs in there because they didn't like that smell. Does anybody know anything at home? Okay, if you have a little bit more money, people would buy a chest that was lined with cedar, the wood called cedar. You know what cedar is? It's like a pine tree. Okay. Okay. And this cedar gives off an odor that insects hate. They hate it. And so they wouldn't go in there. If you had a lot more money, you might have an entire closet that was cedar-lined closet. And in any clothes you put in there, the moths wouldn't get in there and eat little holes in them like that. Okay, well, I thought that was some interesting stories about that. Does anybody have any other stories about phase changes or anything like that? Yes?
My dad showed me an article where they discovered a fifth state of matter in space.
They discovered what?
A fifth state of matter in space.
A fifth one, what's that?
It's like black ice, but it's hot. It's
Ooh.
ice, but it's hot.
If you can give me an article on that,
Yeah.
I would definitely give you extra credit because
Yeah.
I have not read that yet.
Mhm.
I'd be interested in that very much.
Yeah.
And it's in space. I'm very interested in that. Find the article, highlight it, and tell me where you got the article, okay?
Yeah.
I'd love to read that. All right, about ready for some demonstrations?
Yes.
Okay, all right, thank you. All right, so what I'm going to do here, I don't know, this doesn't work great, but we'll try it. Grant, if you're sitting over there, you don't want to sit over there. You want to come over here, don't you? Okay. I don't know if that's going to work or not. Wait a minute. Okay, maybe that'll work. Okay. All right, everybody ready? So we have some vocabulary words in chapter 3, and what I'd like to do is I'd like to help you figure out what they are, what's the difference between one word and another. And so we're going to start out with, okay, we have matter, right? Do you remember in your notes somewhere reading about the word called pure substance? Did you read that somewhere?
Yes.
Okay, and then another word is called mixture. So I want to show you the difference between the two, all right? A pure substance means that it's always made the same way. Now, I'll show you something that has a pure substance. This right here, this is iron. It's called iron filings, okay, little pieces of iron. Everybody see that? Now, that's a pure substance. Any element on the periodic table is considered to be a pure substance. I have another one. Here's another pure substance, and this is called salt. And I think I'll put some in the same beaker right there. There you go. Salt is a compound. How many ways can you make table salt? One. How many ways can you make water?
One.
Carbon dioxide?
Oh, yeah.
One. Glucose? One. Anyway, all elements and all compounds are pure substances because there's only one way to make it. But now, what's what I'm going to do here? What am I making here? Wait a minute. Wait a minute. I see some dark things and some light things in there. What is this called?
Mixture.
Starts with M.
Homogeneous, not heterogeneous.
Mixture. Now, why is a mixture not considered to be a pure substance? Because guess what? Could I have made this mixture having a little more salt? Huh? I made it differently. If you make coffee in the morning and you have coffee, you say, oh, that coffee's too weak. and somebody else makes it too strong, why is coffee never considered to be a pure substance?
Because there's many things that go into it.
Yes, but you can make it many ways, can't you?
Yes.
I can make this mixture of sand and iron many ways. I can make a salad many ways. I can make salt water many ways. A little bit of salt. No, more. That's why it can't be a pure substance if it's a mixture. I think I'll add some more. Here's some sand. Sand! Ah! Oh, too much. Ah, too much. Oh well, I'll mix it anyway. Now, when I look at this right here, I put too much salt in there, sand in there. There we go. But you know what? I can see the sand pieces, the iron pieces, and the salt. I can see that it's made of different things. What word means you can actually see that it's made of more, this mixture that you can see it's made of many things. What is it? Oh, homo means the same. Heterogeneous. This is a heterogeneous mixture. I can see it's made of different things. You get it? Look at your skin. Ah, what is that? It's a heterogeneous mixture. Isn't it? What about a piece of pizza? I see different things, see? Those are heterogeneous mixtures. Now, one thing I'm going to do here, even though I put too much sand in here, I'll do one over. I'll add another compound. This is a compound, H2O, right? Pure substance or not? Right. It is, isn't it? If it's an element or if it has a chemical formula, and water does, doesn't it? Then it's a pure substance. Now, I think I will put them in there. And, whoa, what am I doing here? What are you doing? I don't know, maybe use my finger to do that, but what is that? Somebody said it. Heterogeneous mixture. I can see it's made of different things, can't you? And it's not a pure substance because what? This, whatever's in the beaker is not a pure substance because what? Because how many ways can I make salt, sand, iron, water mixture? How many ways can I make it? A lot. So it can't be a pure substance, so it must be it's a heterogeneous, and it's a heterogeneous mixture, isn't it? Let's try one more. Here's some water. Here's a little bit of salt, a little bit. Uh-oh, keep going. Where's my salt? Where's the salt? It dissolved. Wait a minute. It dissolved. What kind of change is that? A chemical change or a physical? If it's a chemical change, it has something to do with a chemical reaction that took place. If not, it's a physical change. What do you think? What's in the speaker right now? And what was before I mixed them? Then there is no chemical change. There's no chemical reaction. Dissolving is not a chemical change. What is it? And what do you call this now? Oh, somebody. Who said that? Yes. And you know what? A solution is a mixture, and I can make it many ways. It cannot be called a pure substance. Salt water cannot be a pure substance because I can make it many ways. But you know what? You said something good. What do you call a mixture that is homogeneous? A solution. This cannot be a solution. Does that look the same all the way through? No, that's a heterogeneous mixture. This is a homogeneous mixture. Why are they both mixtures? Look at me, come on. Why are they both mixtures? You can make them many ways. Can't you, right? All right. All right. How many ways can I make table salt? One. How about water? How many ways can I make water? One. That's why they're pure substances. Are these words coming together now a little bit?
Yes.
All right. Now, one of the biggest ideas in chemistry is there are many mixtures out there, and we need to separate mixtures. In order to separate mixtures, you have to use properties. There's chemical properties and there are physical properties. Okay, tell me right now, how am I going to separate the four materials in here? Raise your hand if you have an idea. Yes, Sally.
Filtration, distillation.
One more time.
Filtration and distillation.
Okay, filtration and distillation. You remember reading that, didn't you?
And evaporation.
and we're gonna get to that in a minute. I'm gonna do something before that. That's a great thing. You're actually will later do a filtration experiment. I'm gonna do something before I do filtration, okay? Anybody else have an idea how to separate at least one of these things out of here?
Pour the water out.
I could, but then there'd still be water in between the sand, and there'd still be some water in there, wouldn't there? But I like that. And if I pour the water off, ooh, that's a great question you have. If I pour the water off, is it just water? What else might be in that water that I pour off? Salt, not iron. Iron has the physical property of not dissolving in water. Sand does not dissolve in water. Salt does dissolve in water.
Oh, you gotta chemically get the salt out of the water.
Not chemically.
Physically.
All the stuff you read in that chapter talked about how to physically separate things. Yes,
Heat it up.
one more time.
Heat it up.
A what?
You heat it up.
Oh, I could. That has to do with distillation. I'm gonna get there. I'm gonna get there in a minute. But I'm gonna do something before that. Okay, so I have something here. What's that? Oh, sorry. A magnet. Why would I do that? How can this help me?
There's iron.
So what now?
There's iron in it.
Ah, so that's a physical property of iron, isn't it? Now, because I have so much sand in here, I put way too much sand in here. I might not be able to get it out. Roll. Oh, I don't want the water thing. Okay. Wait a minute. All right, everybody see that? So the property of iron, it's magnetic, allows me, the physical property allows me to separate it from the other. None of the rest of them are magnetic, were they? Okay, now we're down to what? And thanks, you had a great idea. Now what can we do? Which one first? Filtration, yes. Now, you'll make one of these later in the lab, but what I have is a funnel, and I have some filter paper. This is the most important thing. So how you do this, you fold it once, you make a taco. Okay, you got a taco? Looks like taco. And then then you go like this. Now, this is where you have to be a little smarter than the filter paper. See, this won't work. Look, oh, that's not gonna filter anything, is it? But if I only peel one layer back, I get even jet stream. Okay. Anyway, so what I'm gonna do is I'm gonna put that in here, and we're gonna pour this, and I want you to assume that I did get all the iron out, even though I didn't. But I'm gonna pour this in here, and so what's gonna happen here? Okay, what is in the filtrate? What is in the filtrate?
Water, salt,
Is that it?
and
And
salt.
And you need to know that when something dissolves in water, it will pass through the filter. Got it?
Yeah.
And so that's salt water. And then we have sand. So I separated the iron and the sand, and now, thanks, Sally, you're on the ball there. What am I going to do to salt water to separate something that's in a solution?
Boilers.
Distillation. Now go to the page in your book, and I don't know what page that is, but one of the drawings you have to do for the next homework assignment is called a distillation apparatus. See if you can find that. Tell me what page it's on. Keep going, it's way back there. There it is. What page is your left hand on?
64.
Okay, so page 65 has a filtration apparatus on it, and that's what I just did. But page 64 has a distillation. So let me show you how that works. This right here is what you see in the picture. Everybody see something like that in there?
Yeah.
So I could take the salt water, put it in a flask, and then I would heat it. Now, why would I want to heat a flask of salt water?
Because you gotta get the salt out of it.
I know, so how am I going to do that? I want to separate the water from the salt. What am I going to do?
Make a gas.
Okay, now we're going to boil the water. It's going to change to a gas. Now, I'll tell you the difference there. If I leave water out at room temperature, the next day there'll be less water there, right? And that is called evaporation. It changed from a liquid to a gas, but at what temperature? Did I have to go to the boiling point? No. below the boiling point, I can still change it from a liquid to a gas, can I? But what if I heat it to 100 degrees Celsius? Then it's called, instead of evaporation, it's called vaporization or boiling. Everybody get that? So now, I got this. What boils? Is the steam going to be just water, or is it going to be water and salt? And I never knew this when I was your age. I never knew this. Only water. Only. If you go home tonight and you have a pan of water and you put a whole bunch of salt in there and it all dissolves, and then you can put it on the stove and let it boil. Let it boil for a while. And boil all the water away. Will there be anything left in your pan?
Yes.
Yes, a bunch of salt. So only the water boils away. That's kind of interesting to think about. Here's just the oceans of the world, right? The oceans of Earth. When the water evaporates and goes up and makes clouds, it doesn't take salt with it. But the clouds turn in and they might rain, and the water goes over the mountains and the rocks and picks up more salt and goes into the ocean. And it, all the water evaporates, and it keeps doing that, and it keeps doing that, and it keeps doing that. Wait a minute. What does that mean as far as the saltiness of the ocean over time?
Getting more salty.
It has to be. Now, there are people who have studied this. They've analyzed salt water 100 years ago, 50 years ago. Get that? Now, I'm not telling you what to believe. I'm not going to tell you what to believe about, is the earth old, really old, or not so old? And I understand there's lots of science shows and books that'll tell you, oh, it's really old. It's like 6 billion years old. But you know what? At least one study, actually it's more than one, if you looked at the saltiness of the ocean couldn't be that old. It would be way, way more salty than it is now. And that's just one evidence, okay? I'm not telling you what to think. But there's no way the ocean could be really old and have all this process going on, adding salt all the time. The ocean would be way, way saltier than it is now. So let's go back to our distillation apparatus, okay? So I turn it to steam, and I push the steam up through here. Now that's going to make this hot steam go through that middle tube. Everybody see the middle tube? Okay, now what you do then is you hook this up to clamps, put a hose here, hook it onto the faucet. Cold water goes in here. Now cold water will never go into the middle tube, but it'll go in this outside jacket. So cold water, whoop, 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 whoop. And then this goes out in the drain. And I just kept having more and more cold water. And what does cold water do when it gets hot steam next to it? What's it going to do to the steam? The kinetic theory says what? I'm going to take away your kinetic energy, all right? Kinetic energy is going to go into the cold water, and the stuff in the middle is going to, what's that word? Condense. This is called a condensation apparatus. And it's going to condense and go drip, 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 and it's going to be pure water. No salt, and all the salt's going to be left behind. You know, there are people in the mountains and other places that they probably didn't even finish high school. They probably never took a chemistry class. But they will go into the woods, and a lot of times they don't want people to know they're doing it. And they'll take some materials like corn, and they'll mush it up, and then they will let it ferment. And then what are they doing there? They're letting bacteria ferment the corn, and it changes it into what? Alcohol. Oh, okay. But now the alcohol is all in this yucky stuff. I want the alcohol to get away from the yucky stuff. So what do they build? They don't call it a distillation apparatus. They just call it a what?
Still.
A still. You ever heard that on movies? Hey, let's go bust up that still. So they have this great big pot, and they're cooking it, and then they have copper. You ever seen the big copper tubes that go like this? Well, why do you need that? Because when that hot vaporized alcohol goes through all that copper loves to give off heat, right? So what's going to happen to the vaporized alcohol as it goes through the tubes? Condense, condense, and go drip, drip, drip. And they have 1 bottle, 2 bottles, 3 bottles. And by the way, that's 100% alcohol, which will kill people. So what they have to do is they have to dilute it. They have to dilute it, and then they sell it. Now, they should be able to sell it. And if they kill somebody, they should be responsible for killing somebody. But the U.S. government does not like people doing this. And do you know why? Because you're going to sell this stuff, right? And how much of that money did the U.S. government get? None. They don't like that. And you see that? You want to sell alcohol? You're going to pay us some money every time you make a sale. So they don't like people selling alcohol and none of the money goes to taxes. See it? So that's why they go out and they find these stills and try to break them up and stuff like that. All right, show you a couple more. How much time do I have? Do I have, what time?
No minutes.
No minutes? Oh, okay. The next time we meet, remind me to show you this right here. Everybody see that? Okay, anyway. All right, well, thank you very much. You have a nice weekend. Now, wait, before you leave, what are you supposed to turn in today? Homework. Okay. Here's a stack right here, and here's a stapler.
Hurry up.